Welcome back, everybody. We're going to start working some example problems here for the normal distribution. Um, we've encountered before already that the claim that 98.6 degrees Fahrenheit is the true human body temperature isn't exactly accurate. Um, in fact, that was the first average computed by a German physician in the 19th century. Later studies have arrived at 98.2% to be a more accurate, so 98.2 degrees Fahrenheit is a more accurate measurement of the mean human body temperature. Um, Now, this will vary quite a bit depending on at least time of day. Your own temperature will change as the day proceeds, age, gender, and the method and location of measurement. Um, the standard deviation, if you look at three fairly recent reliable studies, 0.7 degree Fahrenheit is a reasonable compromise for what the standard deviation would be. So given these statistics, so the mean and the standard deviation, what percentage of human beings actually have a temperature that's less than or equal to 98.6 degrees Fahrenheit? The easiest way to do this, and we're going to be using figure 1 again, the easiest way to do that is to first figure out what z-score goes with that data score. We would like to know what the z is. Well, if we take our x, our data value 98.6, subtract from that the mean, and then divide by the standard deviation, we'll place this score on the normal distribution and be able to find it easily. So we have 98.6. We were told that the mean was actually a 98.2, and the standard deviation was a 0.7. So plug those guys all in. On a test, you would be writing down the formula, the substitution step, and the result that you get out of this. So on my calculator, 98.6 minus 98.2 would be the same as 0.4. Divide by 0.7, and you get a 0.57. So z equals 0.57. Now, we want temperatures which are less than or equal to that. So less than or equal to that means we want to be to the left of z equals 0.57. And when we're asking what percentage, we want the area percentage. Remember, the idea is that the percentage of area equals the percentage of the data equals the probability of that happening. So I made another copy of the figure. I'm going to find z equals 0.57 on the z-scale. Remember that z equals 0 is here, z equals 1 is here, negative 1 is here. That's 0.1, 0.2, 0.3, 0.4. That's z equals 0.5. And that's incredibly messy. I should make that a little bit cleaner. 0.5. This would be z equals 0.6. So 0.57 is somewhere in between those two. If I'm going to do that, I think that for the purposes of this, I'll just round up to 0.6. So this is approximately 0.57, especially since I've got a little bit of jaggedness along the top of this. So I want all the data that are to the left of that Z cutoff. So these are the data that are left of Z equals 0.57. So I'm going to need to count how many rectangles are there. Well, I can make my life really easy if I'll realize that from here down on this half of the distribution, since the distribution is symmetric, there are 200 of the 400 rectangles there. This graph still has 400 rectangles. I need only count the rectangles that are here. And I can make my life fairly simple here if I count this rectangle. This big rectangle is 1, 2, 3, 4, 5, 6 blocks wide, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's 14 times 6. 14 times 6, it's got 84 in it. And then I have 1, 2, 3, 4, 5, 6, 7. I have 7 up there. So 284 plus 7 more would be 291. So the probability that my data is less than 98.6 is the exact same thing as the probability that my Z is less than 0.57, which is going to be approximately, out of all 400 blocks, it's going to be 291. 291 divided by 400 is 72.8%. So not quite 3/4 of the time are we going to find that someone's temperature is actually all the way up to 98.6. Now again, this varies by age, gender, time of day, all kinds of things. So I'll put a little note here, see next page. Now, when you actually show your work for this, I want you to show the region that you're after. I want you to show how you divided this up to get your computation. And then I do want you to write both of these because I want you to realize that these two probabilities are the same. They gave it to us first for data values of x. We converted it into z values, and then we counted rectangles. So show this, then show your answer. Now, this is a little exercise in why we care about z-scores. So Dale scored 100 on an exam. His exam had a mean of 130 and a standard deviation of 16. Alice scored 60 on an exam with a mean of 50 and a standard deviation of 8. Who did comparatively better? That means if we wish to compare what these two exam scores mean. Well, I'm going to divide the page here. The way that we compare two things, first off, we're making an assumption, and this can be a big assumption sometimes. We're going to assume that these are normally distributed. So these are normal distributions, and that can be a big assumption sometimes. But since this is the normal distribution section, we'll go ahead and make that. First off, we'll do the z-score for Dale, and we'll do the z-score for Alice, and we'll compare them together. Well, write down the formula. Z is the x value minus the mean divided by standard deviation. Write your formula down first. That is a standing instruction in this class. Even if I don't write it down on test or homework, you're supposed to do it. Now for Dale, he scored a 100. That's his X. They said the mean was a 130. And the standard deviation was a 16. Well, that's going to be negative 30 divided by 16. It's going to be about almost negative 2. So negative 1.875. It's good practice to estimate what your answer should be. Makes it easier to spot when you've typed something incorrectly into a calculator. Now let's do Alice. The same thing. Z is going to be the data value minus the mean, so we're using the formula here. The data value is her score. She scored a 60. The test mean had a 50, and the standard deviation is an 8. So this is going to be 10, a positive 10 divided by 8, so it's going to be about 1.2. 10 divided by 8, 1.25. Now, if we compare the two z-scores, we see that this is 1.875 below the mean. Comparatively, that's worse than 1.25 above the mean. So Alice is comparatively better. Her score is comparatively better. Now, I included the second question here because people will often go too far in their conclusions. Who is smarter? We have no idea. Because we don't know what these tests covered. We don't know if the tests themselves are comparable. Human intelligence is an incredibly complex, multidimensional thing. There's no way with two tests that you could say that one person is smarter than another. Be careful, because a lot of people out there don't know this, but you should. Now, here's a fairly common type of real-world application for the standard deviation. We're on the border of what's called inferential analysis in statistics. We're not quite there, but trying to predict what could happen, or what more can we infer about what the data are telling us beyond just simply describing. So we have the mean birth weight of babies at a hospital. You could do this at a hospital. You could say 7.4 pounds, and you could get the standard deviation. You'd have the data for all the babies that are born in your hospital. So then you can ask yourself, well, what percentage of babies can we be expecting to have come in at less than 5 pounds? The reason this would concern you is because children which are born under 5 pounds tend to have very serious complications, and if you're a responsible hospital, you want to have some way of dealing with that. So we're once again going to use figure once, because area equals probability. That's a key idea in using the normal distribution. And the reason I have you using that figure is because I want to emphasize and overemphasize that idea. Well, in order to use that figure, we have an X value of 5 pounds, but we would like to convert that to a Z value. We want to be able to, like with Alice and Dale, we want to find out who's exactly where we are relative to all the other data. So write the formula down. X minus the mean divided by the standard deviation. You don't have to use the fancy Greek letters if you don't want. Just write the word mean, write the word standard deviation. If you notice that I've been abbreviating it as std.dev. So write down your formula, plug in. 5 minus 7.4 divided by 1.7. And fumble with your calculator. 5 minus 7.4, that's going to be negative 2.4. Divide by 1.7, so it's going to be negative 1 and change, it looks like. Negative 1.41, which we're going to say is approximately negative 1.4 when we go to graph it on the figure. So here is our figure. Remember, this is a z of 0. There's negative 1. There's negative 2. Negative 1.1, negative 1.2, 1.3, negative 1.4 is right there. And we were asking what percentage of babies weigh less than that. So weigh less, that means that we want to be less than. So we want to be to the left. In other words, we want to be over here. So z equals 4, z equals negative 1.4. That corresponds to x equals 5 pounds. So these are going to be less than 5 pounds over here. So we want to know how much data we have here. Well, if I count, there are 1, 2, 3, 4, there are 5 right there. 1, 2, 3, 4 by 4, there are 16 there. There are 8, 9 there, and there are 3 there. Okay. So the probability that x is less than 5 pounds, write that down first. Say what we're after in the real world. Then tell what we translated that into. That's the probability that z is less than negative 1.4. And then write the calculation. That's going to be 5 plus 9 plus 16 plus 3 divided by 400. 5 plus 9 is 14, plus 16 more is 30, plus 3 more is 33. So 33 divided by 400, we get 0.0825. So approximately 8.3% of our hospital's babies are going to need some extensive care. That means that we need to get a plan in place. And this is actually how you use statistics. It allows you to figure out what's going to happen before it really happens in a big bad way. We're going to repeat the previous problem now using a z-table. So we have to dig out our z-table, which was over here. And we'll have to find a value in the z-table that corresponds to z equals negative 1.4. So remember that what we're doing is we're calculating the probability that x is less than 5 pounds, and that's equivalent to finding the probability that z is less than negative 1.4. Now we just simply need to go to a z-table to figure that out. So lay the z-table down here and let it come into focus. I'm going to find the value z equals negative 1.4. So I read down one of the z columns, and there is a z of negative 1.4. and that corresponds to the 8.076 percentile. Okay, so what that means is that in the normal distribution, if we've got a z as negative 1.4, we've got the tail of the distribution here that we saw a few seconds ago. This corresponds to a percentile that equals 8.076%. That means that 8.076% of data are to the left of z equals negative 1.4. So we could actually say 8.076% of our data are here, which pretty much agrees with what we found on the previous problem. There are actually two commonly used, actually there are many commonly used intelligence measurement instruments. The Wechsler IQ has been around for a while. It's not quite as old as the Stanford Binet. Stanford Binet is over 100 years old. It's normalized so that, and normalized means that the data are rescaled. They change the data. It's like curving a test. They change the data so that the mean is actually 100 and the standard deviation is 15, pretty much. It doesn't always work out that way. So what's the probability that someone's Wechsler IQ score lies between 85 and 115? Well, if you compute the z's for this, so z is x minus mu, always write the formula down first. That's the standing instruction. We'll start with 85 minus 100 divided by 15. 85 minus 100 is negative 15 divided by 15, so you get a z equals negative 1. Likewise, z is an x of 115 minus 100 divided by 15. That's 15 divided by 15. That's positive 1. So that is the data between us here, negative 1 and 1. Well, we can actually add up the rectangles and compute that. In fact, we did that earlier on, but we can use a property of the normal distribution. These are data which are within one standard deviation of the mean. And if we dig backwards to the very beginning of the lecture, we find in the properties of the standard deviation that approximately 68% of the data lie between a standard deviation below and a standard deviation above. So watch out on tests and homework. Sometimes they give you things where the standard deviations work out nicely and symmetrically about the mean, and you can just use these 68, 95, 99.7 values. So there's no real calculation needed there. So therefore, we can say the probability that x is less than this and is less than 115 and greater than 85 is approximately 68%. Now, make sure that you write down this. Write down what what that number goes with. Just don't write down the bare number. Part of mathematics is communicating the result. So this goes with problem number 6. And we go to the next problem. I'm going to stop here. make sure that we don't get these files too big, and we'll resume with this problem in part C.